In this video, we're going to discuss entropy at equilibrium. Many reactions or chemical processes involve an equilibrium between the products and the reactants. This involves reactions going in both directions. Entropy usually favors one versus the other, but we can find situations where both reactions are equally favored. Well, how can that be? One's usually positive and one's negative. Well, let's think about our values here, that the delta S of the universe is going to equal the delta S of the system, so our reaction, plus the delta S of the surroundings. When the delta S of the universe is positive, our process should be spontaneous. If our delta S is negative, then the reverse process would be spontaneous. Well, if they're both as likely, then neither can be positive nor negative. They must be equal. Delta S of the universe must be 0 at equilibrium for the system. Once you've reached equilibrium, your mixture won't want to progress in either direction. Neither will be spontaneous, so the S value must be 0. Neither direction must be favored. Well, in which case 0 equals delta S of the system plus delta S of the surroundings, which we can subtract. The negative delta S of the surroundings must equal the delta S of the system. Remember, the delta S of the surroundings is negative delta H of reaction over T, the negative out front for this one. That must equal the delta S of the system. Negative, negative cancel, so the delta H of the reaction over the temp must equal the delta S of the system at equilibrium. Well, these are values that we can find for a given system. So let's look at a phase change. Let's look at water. H2O liquid in equilibrium with H2O gas. Let's look at this phase change. Well, my standard enthalpies and my delta H of formation values we can look up in the book. 69.9 joules per mole Kelvin for the entropy, 188.7 for the gaseous water. Our delta H is negative 285.8 kilojoules per mole and negative 241.8 kilojoules per mole. My delta S for this reaction, or my delta S for the system, is going to equal 188.7 minus 69.9 for 118.8. My delta H for this reaction, so equal the sum of the products minus sum of the reactants, negative 241.8 minus negative 285.8 for 44 kilojoules per mole. We can actually use this to solve at what temperature we will be at equilibrium. If I know the delta H of my reaction, I know the delta S for the system, I can rearrange this to solve for the temp where these are going to be equal to each other. 44,000 joules per mole over the temp is going to equal 118.8 joules per mole Kelvin. Now, we're using values at our standard states that are 25 degrees Celsius. We're not going to be at 25 degrees Celsius. Well, we're about to calculate it. We should know that water boils at 100 degrees. In general, as long as you're not too far away from the standard state, it's not unreasonable to use the standard state values, but they often are subject to change with temperature. So as a result, when we calculate this, move our temp up, move our 118.8 down to solve at what temp these should be equal to each other, we find 370 Kelvin, which is about 97 degrees. So very close, but slightly off. Why is it slightly off? We need to increase our temperature by about 75 degrees Kelvin over where our enthalpy and entropy values were actually calculated. As a result, they are slightly different. Obtaining those values at other temperatures is much more trouble. Our table is for standard state, but it is possible to find them. What we'll find if we look is that the delta S for liquid water at 100 degrees is 86.8, while our gaseous water is 195.9. So they are slightly greater. Well, this would affect our value a little bit. In fact, our delta H is a little bit different. Really, this process is vaporizing. So our delta H of reaction here is really supposed to be the delta H of vaporization. Well, those values are actually calculated at the temperature of vaporization. And so if you look up the value for delta H of vaporization, normally it's 40,700 joules per mole. Close, but off by about 9-ish%. So the assumptions that we can use the standard state values at other temperatures works a little bit, but the further from the standard state, the more inaccurate it becomes. If we want to reorganize and try with these new values, well, we can calculate out the delta S of the system at 100. That's going to end up being 109.1 rather than 118.8. Plug that in, 40,700 over the temp should equal 109.1. Rearrange to solve for that temp. We find 373 Kelvin. But this is the temperature where our change in entropy of our surroundings should be equal to the change in entropy of our system. As a result, neither is favored anymore, and we are at equilibrium. And indeed, at the temperature 373.15, water, gas, and liquid water will change back and forth into each other freely. In a well-insulated system, the amount of each would remain constant. While individual molecules might change from one phase to the other, they'd be replaced by another molecule doing the opposite transition. Neither direction is favored, and they will occur at the same rate. So using this relation, that the delta S of the universe is equal to 0 at equilibrium, can help us find useful information like the temperatures at which a phase change would occur for a material.